collider. Electron-ion collider designs, or are you banking on there being China and
basically EIC. I will not discuss that.
First slideshow or full screen?
Full screen.
plural needs more than zero.
Yeah. Okay. Good. So I was given the talk of nuclear PDFs and electron-ion colliders, but I will only be discussing some EIC things, not LHPC or possibility of a Chinese electron-ion collider that we all know can happen. So before I go to the outline of the talk, let me try. Yesterday we talked about PDFs, EMC effects, everything was nucleus. So let me try to tell you why nuclear PDFs are important, and I will say this in any kind of talk, whether it's most of the audience with PDFs for protons or no one is an island, no perfect distribution function is an island. We can obtain proton PDFs from EP and EP collisions. We can obtain fragmentation functions from E plus and minus. The minute we want to add here EP or PP data, we need a proton PDFs. Then if we do nuclear PDFs, we also have neutrino nucleus, electron nucleus, proton nucleus interactions, and some of the data like neutrino nucleus and electron nucleus can be used for proton PDFs. Then we have a connection here. We also use particle production in vitro gold data for the nuclear PDFs. Therefore, we are connected to the fragmentation functions, and there are hints that there are nuclear effects in the fragmentation function. So we may get everything connected, since we need, in order to determine this, we need this. In order to get this, we need this, and then everything is connected in the end. And this is not even considered AA. So it's very important to realize that if we modify somehow with our data and our studies the nuclear PDFs, we will have an impact on the proton ones and vice versa. So the outline of the talk is very simple. I will briefly go over things you all know, and if you don't know, that will be very odd because you heard this over and over again. And then I will try to discuss what's been done with the data that we include in our fits and how we do our fits that have an actual impact in the final result. I will briefly compare the nuclear PDFs, and then the last part is actually what can we do at an electron-ion collider. So things we all know. First things first, this has been being measured for many years. 1983, first time it was published, neutron current BIS of nucleus, but there are actually data from 1981 that are with charge current. And this is ancient history. It's 37 years old since it was published, which means it was measured even before, maybe about 40 years ago. To me, that's ancient history, so older than me. And if we want to maintain our partenic description of the nuclear collisions, we have to accept the fact that particles behave different in a nucleus than in a free proton. This is one of the original plots where you see the anti-shadow ENC effect and then the rise of motion. And of course, it is not well described by this thing. So how do we do this? We have factorisation theorems. Factorisation theorems only work for protons, not for nuclei. We don't know if it works or not. It might be that we are just feeding data and we can just destroy the data, but it's not fully valid, or at least not in the full kinematic space. We know about proton PDFs. We use the same ideas, same ways of performing a global fit to world data, and usually we parameterize the proton fit of the parton in the proton in the nucleus. We use isospin symmetry to determine how the partons in the neutron in the nucleus behave. We combine everything and we get the nuclear one. Does this mean that nuclear PDFs are a done deal? But this is the way we do it, like for protons, and then the nuclear are the same and everything is fine. And as I said before, we don't know if this factorization is valid, not entirely. We don't know if this isospin symmetry we are assuming is still valid. And there are many things we don't know, unfortunately. So the step for a global fit, we all know, is take the data, write your PDFs in terms of some free parameters and some initial scale, give value to the parameters, determine this distribution at the experimental scales using the evolution equations, convolute this with the hard part of the observable, put everything together to obtain a quantity that tells you how good your description is, modify these parameters until your description is good enough with some criteria. And then we obtain uncertainties for this, theoretical uncertainties, and provide people with open codes to use. So first of all, what's up with the experiments? What's up with the experimental data used in the fit so far that have an impact? Well, first of all, there's the issue of the data. Quantity of data, kinematic coverage of data. For the proton, this is for NNPDF 3.0 NLO analysis. And I only picked this because I already had the plot at hand. They have more than 4,000 data points. More than half of this is neutral current DAS, 20-something% of this is charged current DAS. And they cover down below 10 to the minus 4 in X, and almost 10 to the 6, 10 to the 60 something in Q squared. For the nuclear case, it's much worse. It's barely a bit below 10 to the minus 2, depending on the kinematic cuts applied by the people working per feet. Doesn't go much above 100 GeV square in Q. And then some data from LAC sit very high in Q square. That's very nice, but these are like 17, 20 points, not much. The total amount of points is less than 2,000, less than half what the product PDF have. And it's divided in many, many nuclei from A equal 4 to A equal 208. So as you see, we're in a much worse situation than they are. But there are not only problems with the fact that we don't cover a big part of the genetic space or that we have very few data points. There are things involved here. One of the first issues is the fact that we have most of the data has been published as ratio of the structural functions with respect to the structural functions from other nucleus that could be carbon or deuterium. And that's an issue because F2 has little sensitivity to the glucose if I write it leading order or next to leading order for fit. And this F2 extraction is usually based on the parameterization of the longitudinal to the transverse cross section. So the usual way of doing this was saying, okay, R is some phenomenological parameterization of that the collaboration obtained. But I've seen other things like saying R is 0.2 for every nucleus, or R is 0. And then the same collaboration provides you the F2 ratios, assuming R is 0, assuming R is 0.2, assuming R is some parameterization, and you stare at it and say, what do I pick? Because these people are no longer around, at least not working on these things, they probably don't remember what they did. So what do we do? Okay. Some actually are not ratios of F2, are actually ratios of cross sections, but you have to really carefully read your papers because sometimes the tables are labeled wrongly. Are there any R data? Yes, there are some R data. I was doing a bit of archaeology, and if I put a cut of Q square above 1 GeV square, I get about 80 points for this ratio. We don't use it in the fits, but it's there. The data are there. Are there non-ratio data? And this was discussed yesterday about the possibility of measuring just the structural functions. Yes, there are quite a lot. About 900 points for F2 in deuterium, in calcium, in carbon, and in iron. And I think maybe tin also. But it's not used. They are not used at all in the fits. Could we? Yes, in principle, yes, but there are some issues with the normalization for some of the data. Not all of them, some of them. And then most of the data has been corrected for non-scalarity. And sometimes it's not so easy to find how to undo the corrections. And actually, I can provide some papers that do not even tell you how to undo or do not even tell you if there are any corrections. So we have to assume that's the real data and deal with that. Then we have, that's for neutral current. For the Brownian, we have some problems in the fact that, so it provides some constraints on the C, that's why we use it, but there are not many data points. It depends on how we select the data, but it's 90 to 120 data points. And basically, instead of giving us ratios, that means it's next to leading order or next to leading order corrections for the cross section become less relevant. This is a fit with the leading order from the AKS. This is a fit NLO from the latest EPPS16. As you can see, the ratio has a very similar shape, but we didn't certain this if NLO modifications are relevant or not. The latest analysis, EPPS16, included some very old data. You see 1981, 1987, 1989. But this is doing collisions between pions and tungsten or pions and platinum. And there you have an extra source of uncertainty, which is knowing the PDS for pions. And as far as I know, they are not kept up to date. So it's a very old, rather old fit that you have to trust to work. Then we have particle production at RIC. Pion production at RIC has been included in nuclear PDF fits since 2009 in order to improve our sensitivity to gluons because there's nothing from the neutral current or from radiant data. So it's wonderful in the sense that it's sensitive to the gluon density. It's terrible in the sense that the uncertainties are relative. So as you can see, you don't constrain much with this. And they also depend on the permutation functions. And permutation functions are not as well known as proton PDFs. So depending on which permutation function you put there, you can get very different results. And then there's the question of whether or not there are finite state effects. Because either there are finite state effects, and we are doing it wrong in the fits by not taking those into account, or Hermes measured something very wrong. Because this is the ratio of the semi-inclusive to the inclusive BIS of nuclei with respect to the same observable deuteron measured by Hermes. And as you can see, there's a very relevant effect, except when Q square is quite flat, but everything else has a very strong dependence. And there's no way you can describe this with a nuclear PDF. You can try, I tried, it's impossible. You get a small effect, but you cannot describe this big benefit. However, this is has been only been measured in Hermes. We need something to cross-check this. EIC is an idea. And then there's the charge current data. And charge current data has some issues. So let's start historically how this come. Their data has been measured many years ago. And then we have newer data to 1991, 2006, 2006. And I forgot to put the reference here, sorry. So about 2008, 9, more or less, some of the people that now are part of the SIGTEM collaboration, they did a fit using NUTEP data. NUTEP data with the full cross section, okay? Because NUTEP also published the structural functions. And it turns out that this nuclear effect seems to be incompatible with neutral current nuclear effects. The ratio is different. This is for charge current, you see, and this is for the neutral current. And then when we did the analysis in 2012, we included the NUTEP data, the chorus, and the CHSW, but only as structural functions, and we didn't see any kind of function. And now EPPS16 included only the chorus data because there was this controversy with the NUTEP data, and they have no issue. So where's the thing? Well, the ratio, I was not surprised that it was different because the combination of PDFs that enter in F2 for the charge current is slightly different than for the neutral current. So there has to be some difference there. There's no proton reference for these experiments. So the ratio, or deuteron either, so that ratio you have to construct with the denominator. And the tension appears with NUTEP data only if you consider the cross-section and only when you consider the covariance matrix. And it's true, NUTEP data is very precise. Chorus data, even if you take the cross-section and the covariance matrix, the uncertainties are very big, so it really has little constraining power. But the fact remains that EPPS16 managed to include chorus data with that. So this is an open issue.
What do you use?
Chorus is lead, and the others are iron. So in principle, this is an open issue. Because if you have one experiment, which is CTHSW, in which it's only the structural functions. Well, there's cross-section, you put it there. Yes, you can do the fit. There's no covariance matrix. You don't have the correlation between the uncertainties. You feel no tension. You have some tension only in one of the two experiments you're considering. I don't know to what point one can really say there's a big difference between nuclear effects in charge current and neutral current, or it's something that comes from the measurements done. So that's something that I honestly think should be cross-checked in a new experiment. Because this could have a huge impact. If we go back to my second slide, it's saying that everything is connected. Charge current DIS is used for determination of flavor decomposition in proton PDF analysis. So if we are putting there some nuclear effect that is not right, that is not compatible, we are really doing something there.
But wait a minute. So what in your fit, do you let the nuclear effects being different for the different flavors?
In my fit, the nuclear effects were the same for valence, the same for all the C, and not for blue, because we had no sensitivity.
No, I understand why, but so.
But in EPPS16,
this problem comes from that.
No, what I'm saying is the issue seems to be some tension between different datasets.
Yeah, I understand.
And then for proton PDF analysis, they do allow for flavor composition, and they include muted data or coarse data in order to have sensitivity to different flavors. Because neutral current data does not give it to you, and higher charge current data is very scarce. So they add this data because you have 1,500 data points from the charge current, from the neutrino charge current.
So this positive ratio, this small enhancement in what?
This one?
Oh, the slide is not. This x ratio larger than 1.
Yes.
Comes from what?
Okay, this is not exactly the best way to show this because this is not the ratio. The data here is being presented in this particular when it's combined. With every data you have in the certain energy beam is combined with different near-skin elasticity, so it's not the best way. But it seems to prefer some sort of enhancement, and this is really.
My question was, since we have the feed, you can see whether this enhancement comes from values or from sequence. True,
but I'm not the one who did this analysis in particular, so I cannot give details on the final things on the analysis. Mostly, this is dominated by the balance. By the balance.
Yeah,
because it's basically balance. It's the same as neutral current because we are still in a region where the balance dominates.
No, 10 to minus 1, C and
okay, and then there's the other thing. That's the other thing. But this is ABPS16 analysis, and for them, the enhancement on the balance, the C, and the gluon, okay, the anti-shadowing, it's sort of incorporated into the parameterization. They feed the ratios, assuming there will be a minimum for the EMC effect and a maximum for the anti-shadowing. And that's something that is encoded in their own parameterization.
Okay.
So it's a bit artificial in that regard.
Okay, fine. Thanks for the.
Okay, so that's for the data. There are a lot of data that are not included in the fits for different reasons, such as jet data from Atlas in either collisions, because it's 0 to 90 centrality, not bias, and we have enough sources of uncertainties that we don't want to add more. So what can the person doing the fit do to that impacts the final result? That's why I'm free. I do the work. I can pick to do whatever I want. So I can pick my data. I can say, okay, I will take the ratios. I will take this F2, which we already did. I will take the cross sections. What type of data I will consider? Will I remove these corrections? How will I impose mathematical cuts? How will I treat all the theoretical things that enter into the calculation? So when I do my parameterization, I usually take a proton PDF as reference. So that means I would like to start my evolution at the same point as the proton PDF reference I take. I will try to treat the heavy parts accordingly, which is not the same thing. And I will try to impose the same kinematic cuts, despite the fact that sometimes we don't do that because we throw away too many. And then we have to do the actual parameterization. Different ideas relate the nuclear PDF at initial scale to the proton one times the factor where all the A dependencies is incorporated, or write the nuclear PDF as the conclusion of the proton one times the weight function. And this is very, very interesting because this was the first analysis done in the next leading order, and it allows for it allows to reach x between not 0 and 1, but from 0 to 8. So it allows to go beyond x equal 1. However, they never included the data into the few available data points into the fit at the time. And then the other way that has been done recently, lately, is to directly parameterize the nuclear PDF and require that for A equal 1, they recover the proton 1 as reference. Then I have to write my theoretical prediction once I decide how to do all this stuff. So I choose an order, leading order, next to leading order, next to leading order to go. I need to understand clearly what it means in terms of alpha s, because some people call leading order alpha s to 0, and next to leading order alpha s to the first power. But some people say, okay, leading order is the first non-zero contribution. So that means that, for instance, for the longitudinal extractor function, some people call leading order something that's order alpha s. So you have to be very careful to how you call what you call and be clear about that. And then how you treat heavy quarks. There are many ways to treat heavy quarks. There are fixed flavor, zero mass variable flavor, general mass variable flavors, different ways of applying this. So just to compare, this is from the X terminal. This is the Robert Thorne's scheme. This is one of the atom type schemes, and you can see for below the heavy core mass and above the heavy core mass, which charm or bottom final state diagram are considered. Here we have Fred, who's one of the authors of this below. And as you can see, it's very different what you're considering. So this also has an impact. It's true that we are probably not that sensitive to the heavy quarks right now in the nuclear PDFs, but we will be. And this will have a huge impact. Then, do we consider or not nuclear effects in the neutron? That's really important. We are not that there are nuclear effects in the neutron. We usually don't consider them for the actual fit because it takes forever. Then there's this issue with the finite state and hadrons. Do we use them? Do we not? How do we use them? Do we have any? So far, they're only included in the SSZ. When we did the analysis, we did the fit with and without the nuclear effects for the fragmentation functions. And that changed to 25% the chi-square for the break data. However, break data is less than 70 data points in the case has 1500. So this is a variation of the chi-square at below 2%. It has no impact, despite the fact that, as you can see, from this flat curve without effects to this very deep depression IPT, it's a very, very different shape. Then we have to put together a chi-square. Chi-square we can write in different ways. But the most relevant thing is that we are missing most of the time the covariance matrix and lessons learned. We all know that knowing how our uncertainties are correlated is very important, and it had a very huge impact on the result. Can we do it now? We can, because we don't have the covariance matrices at the time. They were not published or they were not determined. Now we know they're important. We should try to do that. Then we actually have to do the fit. How many parameters we put in there depends on many things. There are many. It's very hard to determine the absolute minimum of the fit. We have poor sensitivities of some flavors. One thing that has been done, for instance, is to give relevance to certain data sets in order to enhance the sensitivity to some flavor. The clearest example is EPS09. They took the weight data and they put there a weight factor of 20 in the chi-square to make the sensitivity to a gluon bigger. And as you can see, this produced this huge anti-shadowing EMC effect that was a typical result for EPS09. Why compared with MBS or BSZ, which have a much flatter gluon, has a really completely different shape, and it's all coming from this weight added into the data.
What drives, say, shadowing for valence?
Shadowing for valence scores, well, for which analysis?
Oh, this one.
Okay, so for the green one here, the green bands and everything that's the SSZ, it's basically driven by the momentum conservation rules, the charge conservation rules, sorry.
Very good.
This balance charge for valence, U-valence, anti-valence.
Momentum sample doesn't.
What?
Momentum sample doesn't.
The momentum sample, it's used for the gluon.
Yeah, but here, basically, it's from shape, from Bayesian charge.
For the balance, it's yeah, you get the balance charge. We require the integral of the U balance to keep 2, the integral of the P balance to keep 1, and that's how you constrain the balance of loads. In EPS 09 or EPS 16, they require that one of the parameters in the fit is saying that this becomes flat at low x. So they force the shadowing in a way. Because you have to do something, otherwise your fit has 80 parameters and you will never find the.
Oh, I'm surprised that it's so much.
Yeah, but it's very artificial.
It's very artificial.
And I will show in a few slides how artificial this is. Just then, how do we determine the theoretical uncertainties? We usually do a quadratic expansion around the global minimum. This is not always enough. Sometimes you have to go to higher orders. And the important thing is, in order to determine uncertainties, basically what one has to do is allow for each parameter to move a bit without spoiling the quality of the fit. How much we allow each parameter to move without spoiling the quality of the fit depends on what we call spoiling the quality of the fit. That's the choice. Some collaboration use 50 units in the chi-square, some collaboration use 20, some use 30, you can use whatever you want. That's another choice, therefore, another source of uncertainty. So, comparing nuclear PDFs. Everything that you see from this orange line to the left is an extrapolation to trust. There are no data there. Actually, some people put an even higher cut in their Q square, so this line moves to tiny bit to the right. Anything there, don't trust it. The same way it goes 0.8, 0.9 in X. Don't trust it because it's an extrapolation. This is balance comparison, U balance compared to D balance from EPBS16 and NCTEC15. Two colorations that try to separate the nuclear effects for the balance, and you can see the results are completely different. Why? Well, the most simple explanation I find is NCTEC15 only uses neutral current. EPBS16 has neutral current and charged current. As neutral current DIS for the proton or nucleus, as we know, only constrain a particular combination of up and downs. If you only have this, you cannot really disentangle U balance and D balance. If you only consider neutral current, you need to add something else that will give a bit more sensitivity to a different combination. But if you take the average, everything is compatible and makes sense. Just like that. If we compare the C distributions, as you can see, EPBS16 has huge uncertainties. This is because they wanted to allow for flavor separation, which means allowing for more parameters into the feed. And if you have no sensitivity, your theoretical uncertainty is global. Unfortunately. But that's the price to pay for more freedom in your feed.
So if I can add,
yes.
For CTEC, we actually, in that fit, our string is tied to the U.
Yes.
So we don't have the full, so.
You don't have a full, you
yeah,
don't have it in the balance.
Right, so that's definitely an underestimate. The larger ones probably was true.
Yes,
yeah.
Exactly. And actually, I have to say, EPBS16 began the paper saying, we want to have full flavor decomposition, but then you go to the fit, the table in the paper that has the fit parameters, and you see that many of them has been tied together because you have no sensitivity and you cannot really impose full flavor decomposition because it never converges.
Where from any constraint comes from strange.
That's the thing. It's artificial. There's no
Because
real.
you said extrapolation starting from this point, that I would say I would put this line all the way to the right.
Well, the cut is for the data. My orange cut means there's no data on this side. But you're right, the
Okay,
data is not
relevant
sensitive.
data.
There's no sensitivity in the data to the strange. That's the clear stain you get from this plot. We don't understand the strange. And then we have the blue one, which, as you can see, it's completely different no matter what. So let's do this. This is the first analysis, HKM 2001, living order, first analysis ever actually performed in a fit with nuclear data. And this is the shape they got for the blue. You see? Nothing to do with colors. Then we have the blue line here is NDS, which was the first analysis next to living order. And as you can see, where we have in the region where there's actual data. Yes, that data is not very sensitive to blue ones once again. It's compatible with UNIT, or more or less. They don't have uncertainty bands in that analysis. Then EPS09 with the huge suppression and enhancement that is artificial, as I said. DSS has everything compatible, almost everything compatible with Unity within uncertainties. That also depends on my tolerance criterion, how much I allow my feed to be spoiled or not. So this is a factor of 30, 30 units of chi-square. The DSS set is 52. That's also a reason why they have to figure that. And here we have a comparison with EPBS16. As you can see now, everything is compatible with Unity. And in the case of NCTEC, they also have a huge enhancement and a suppression. But once again, their sample plans are to be conclusive about anything. However, despite the fact that everything looks so different at the level of the PBS, we all keep nice description of the data. So this is the ratio of F2 in calcium with respect to deuteron by NPS, AKM, NCTEC15, Ka15. This is an excellent linear analysis. EPBS16, HKM7, DSS. We all describe the data very nicely. And as a good reminder to all of us that the physical observable is what determines everything. The PDFs are a mathematical object that, yes, have some physical interpretation, but in principle, you can have a complete different shape and still describe the data well. Okay, so next part is what can we do with ANIAC? So I modified this part last night because I got a couple of ideas. So there are certain things that we can do, no matter what collider we get, where we get, etc., etc. The most clear one is extended kinematic coverage. I personally prefer to have an even bigger kinematic space because I do PDFs and I really want to explore my space. Other people would like to explore other things. Okay. Whatever we do, we get a bigger kinematic coverage, which is always good. We got more data, high precision data, and non-modified data. So we can convince the people who do the analysis to please publish everything as it is. If they want to include non-scalarity corrections and blah, 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 we welcome to do that, but please give us the real thing so we don't have to surf through papers to figure out what are you doing. We can get all data. Instead of just structure functions or ratios of structure functions, we can get the cross-section, the structure function for F2, for FL, for the heavy quarks, the cross-section for the quarks, the structure function for the heavy quarks, both FL and F2. So we get everything and we can test several things. We get level arm in A. I don't know how doable this is at LHEC if that ever happens. Someone told me, oh, they're playing around with xenon for LHC. Yeah, xenon is not a light nucleus, right? It's quite heavy. So I think EIC has more possibilities for studying different nuclei from light to heavy. And we can try to convince people to actually please publish various methods now that they know they're relevant. Then there are things that we know how to do, that we have been doing. Things like study neutrons, and that was discussed yesterday. There are a lot of studies using deuteron to study actually neutrons over helium-3. That's something we can continue doing, but of course by the time EIC arrives, JLab will have to prove our knowledge of this greatly. We can study inclusive cross-section, so we did this analysis and published last year. This is simulated data for EIC. For 10 events. I think that Salvatore will talk about this a bit tomorrow, and Julia will discuss this on Friday or Thursday, depending on where the finishes. And we studied how much this would impact whether we have a low energy range for the machine or a high energy range for the machine. And as you can see in the blue ones, we have a relevant impact in both cases. It's a bit better for the high energy version because we can go lower in X.
Why are you stopped at 0.5? Why there is no?
There's no pseudo data in the simulation above 0.5. Salvatore?
Because that is the energy range that you facilitate in the plot that you measured. So the lowest, the highest in X that we reach there is 0.5, let's say.
So what happened to that?
What happens about?
Why couldn't you run 0.6?
Yeah, we have to run at lower energy in central mass.
Okay, that's what I want to understand. What energy?
I think that I'm not experimentalist, so I can confirm it, that it should be lower than.
So it should run at 20, right? Our lowest energy there was that one. You should run around the real lowest energy.
Okay, so basically your statement is with this design, covered with the S31.6 is lowest we can go with some reasonable luminosity. So large X not possible beyond this one. That's basically okay.
Sorry, can you say it again?
To measure larger X, we need square root of S smaller than 31 G.
Yeah. Otherwise, you don't have a sensitivity in the cross-section.
So that result is that basically large X physics, like what we discussed yesterday about EMC effect, cannot be done with this type of configurations. Okay.
So can you go to lower energy? Yes, I mean now we consider, I think, starting from 20,
Yeah, but at some point there's big overlap.
But then you enter the domain where already experiments.
And if there's a big overlap with JLab,
I mean, you have this lines of energy somewhere.
sorry, here.
I think this is.
So this is JLab 12 and the
green is
lowest.
JLab 12, right?
Yes, the green is JLab 12. And here is the lowest.
Yeah, but this is squared, you don't see the X stuff.
Square root of S for JLab.
The square root of S, this is 30.
JLab is 5.
Right.
So it's well below 30 G.
Oh, sorry, no, this is 15 to 40. But this is an older plot. This is taken from.
So then you have some overlap. But also, when you go to the very high X region, I mean, those figures, you don't see what's going on. I mean, how can you really compare? And the limits is also very dependent on the detectors.
Yeah.
So
Sure. Well, it says what it assumes, right? It says 0.01 in Y in elasticity 0.95.
no, because here, if you look at the gray area for the EIC, it goes up to 1. Because it doesn't account anything about detectors.
That's right.
While the part of JLab is
It
got
does.
some.
Yeah, sure.
No, that's right.
things,
That's right.
Which is incorrect because at JLab
Yeah, but we don't have a
go to
detector.
integrators and all.
You know, I mean, we don't
No,
have
no,
a
no,
detector.
that's-
What do you want to do?
But it's not.
It just shows the kinematic range.
That's correct.
Yeah,
That's correct.
But that's what I'm saying. So
The
with
rest
this
is up
figure,
to
we
the-
cannot compare this.
No, it just says what kinematically is possible, right? The rest is a question of the
So
Whether or not it's.
X of
And
1
yes,
is always possible.
and of course, well,
So it's also a question of, precision on reconstructing Q-squared X. And so we have to look at both lepton methods and hadronic methods.
Combine. For light checks, you always combine this. You cannot do it without.
Yes.
combination.
So,
I mean,
there hasn't been very much study
you know.
of how accurate that the hadronic method is with a realistic detector or with the detectors that were designed. That's an important study to do and to see whether there are
Yeah,
changes that would improve
whether
it.
you can do it with prop Newton the same way as with heavy Newtons. When we discussed yesterday this whole IMC
Yes.
tagging, that's basically goes into.
And tagging is another story, but for sure, if you have the problem will be that you're producing, when you're at very high X, the electron goes on the side of the hadrons.
Hmm.
So you will have a ton of background. Because you're producing a lot of stuff on that side.
and you know, it's hard. I mean, let's not forget these points are all, including the green area, is all fixed target. Okay? And there, it's a different thing. And yes, he's a collider. So there are different rules applied.
Yes, exactly. And that's why I was asking
I
this.
mean, the low PT 0.01 in elasticity, you know, is already going lower. It's just that the electron, you know, just goes through the E pipe more or less.
So, I mean, the general question is how much is it needed to get into that corner? Seems it's very important. And what actually is needed? Which is not so much, it's a little bit about the PDF fitting, but I think it's much more about precision in these hadronic methods than defining
Yes,
execution.
because electron-only method will give you good resolution for Y up to 0.1.
Yeah, then you need from that.
But this
Then
is,
you
but
need
it's
some
but
hadrons.
yeah,
but this is not the limitation. The limitation is not the Y. The limitation is that when you go to high X, you start to go to small angle. And you're
Yes.
just going in the small angle where you produce all those hadrons and they
And
can
you
do
need the
second
same
decay and
What
give
you
you electrons
What
themselves.
usually can
So
envision
now-
is to put some tracker or silicon tracker around.
No, but the problem is not to
Forward
detect it. Let's assume you do detect it. Now, how do you differentiate an electron that comes from a
This
decay of a
comes-
hadron and an electron that is your scattered electron? Knowing that your
so-
scattered
So
electrons
electron
are
that's
highly,
very
highly
high
suppressed.
It would be very, very high energy.
Yeah, exactly. So
Yeah.
usually.
So the
But
secondary
the hadrons
electrons
will be
There is
really
separation.
high energy
Yeah,
as well.
and here is exactly
They are
where
exactly
we need
the same
very
energy.
good electron-ion identification. And this is exactly where TRD will help.
No, no, no.
This is,
I started this discussion, but
This
I'm
is
gonna
what I
end
need
it.
to-
We need to let the speaker, this is outside, we spoke for talk.
I had a
So,
question, but I
Raphael.
can ask them. I have a good question for experimentalists that will come up. Okay, so this is the kind of thing we can do that we have been doing. This is basically our base for the nuclear PDS fits. It's using neutral current PDS. But of course, here we could consider the cross sections directly without any ratio, that would be great. Things we know and we have not done that we know we can do is determine the reticulated structure function, and it's something we can even do for the proton, which would be a great advantage with respect to Hera. If we go to high energy, maybe we can, I'm not experimentalist, remember that's not fighting, achieve some flavor of the composition using charge current, maybe. We can explore very flavor schemes, the possibility of intrinsic charm, we have really precise data. Check for final state nuclear effects in semi-inclusive DIS, and if they actually exist and we confirm Herman's result, determine them in detail. That would be very interesting to me. There's the other thing at centrality. How does centrality relate? How is centrality related to geometry in this collision, these kind of collisions? Can this actually allow us to reach a high density nucleus effectively? And here's a very interesting paper from Aschenauer and collaborators. We can study helical cross sections that we have never done in a nuclear case because we never convinced people at the time. So this is our simulation from last year's paper. So again, Salvatore will discuss this, Julia will also talk about this. And what we see is that through photon gluon fusion, we can access the high X in the gluon. Whether it's a lower energy version of the machine or a higher energy version of the machine, at the highest gluon, we can improve our knowledge tremendously. Then we can include jet data. Yes.
Which essentially answers Mark's question, right? I mean, to nail down large X, we don't even have to go through all this brouhaha. We use charm. And
Yeah,
so
but
this
here
is
you don't
still
constrain at 0.7.
And it does have
yeah, okay, but it goes up to what is it?
0.3.
0.3.
Yeah, I mean, if you have more
Oh,
luminosity,
this is
0.5.
Oh, it's a little bit question.
It goes to 0.8. Sorry.
No, you look at the
Look at where there is data. The fits are just extra.
So with the inverse Ventover basically went down to 0.3 until we lost without statistics. So
another question
That's
is
one.
0.5 point of why
Can I go?
Yeah, go on.
Good. Then I have a question, and then you can discuss over lunch with my question. Another thing that can be done as can be proposed, and these two papers are really good and interesting, is to use jet data in the analysis. So far, the only jet data has been included in PPS 16, the digits from CMS, but this works from Glass and Kovarik and other collaborators show that, okay, this is the pseudo data, the points are the pseudo data for EC. The bands are the predictions with two different nuclear PDFs. As you can see, the uncertainty bands for the theory are huge compared to the experimental predicted uncertainties. And this dashed blue line tells you how much of the total cross-section is coming from gluons. Okay, so as you can see, in the case of jets, which is this plot, at low X, most of the cross-section, more than 50% of the cross-section is given by gluon processes. So it allows you to go into the lower X glue. And if we look in the case of digits, more than 50–40% of the cross-section and the higher X is access to glue. Okay, so those papers are very detailed and interesting.
What PT?
Yeah, I don't remember the numbers. Everything is in the paper, for sure. But sorry, I don't remember. And then there are things that we don't know. We can study up to which point our factorization is valid, at which point this isospin symmetry that we assume is valid is truly there. If there is new phenomena or not, we could try to figure out to maybe reach it. Study nuclear GPDs, TMDs, etc., etc. There are other observables that we never use for PDF fits that seem to be very interesting. Most of them are very model dependent. That's why usually we don't put them into the fits. And anything else you may think of can be studied at NEIC. So going back to one of my first slides, everything's connected. NEIC would be a chance to make everything from scratch the right way, having lessons learned from all our past experience. Thank you. And now if I may ask the question, I want to ask the experimentalists and then you fight over lunch for this. What would happen in the high X region if by the time we built an EIC, the data are measured, analyzed, and published, that takes forever? JLab has thoroughly studied the high X region.
This is that they would have characteristic effects.
Then there will be other things to study. That will be interesting. But if we kill each other over,
But nuclear PDFs, I mean, nuclear effects are more strongest at smaller cubes.
No,
It's
but
super
the
high
question
cubes
higher
where
twist, which
this,
is correlation.
all the nuclear effects start.
Oh,
to
that's the
affect
problem that we discussed yesterday. That for large X, characteristic effects are large. Actually, it's a question to you how we treated slack nuclear slack and general nuclear. We took PDFs or nuclear PDFs and multiplied by ratio given slack.
And one of the root of the problem,
Oh, but basically, let me put it more provocative. My statement is, if you would do one, take ratio from slack, take nuclear PDFs, anybody, and fit cross-section data, it's slack. You would fail. Just because the characteristic effects, when you go down, the two square become more and more important. And one normally doesn't include this data in the proton field, for instance. Basically, simple thing is that, say, people studying PMC effect was presented yesterday, observed that when they fit relevant general data, they get X dependence 1.6 squared. You take CTEC or any parameterization for the same Q square, you get roughly 1.6 Q. That's understandable.
But I mean, at some point you have to face reality, okay? I mean, large X and very large Q square is an experimentally really tough region.
no,
Yes, it is.
IX is always high Q square. So it's high
No, it's not. What are you talking
the
about?
cost
You
of
can have
counting
high
it.
X and no Q square. Jesus God, I mean, look at the bands. I mean, there is data on this, it's like, we were talking about this. I mean, he was afraid that, the large X data is not enough large Q square. It is a difficult area,
Yes.
right? And I mean, for fixed target, you have your own issue. For a collider, you have your own issue. I mean, if there is a really thrilling, absolutely blue, physics point, which goes beyond, I can do higher twist, or higher twist effects are small, then I think you have to come up with that.
Well, but basically, maybe if I look broadly, I don't know, I can't understand whether the only chance for the precision measurements of large X, about 0.5 up to 1, fixed time. Just done well because
That could be, but
Well,
look
we
at
need
the
to
EIC aims and gluons. Gluons
Yes.
are not at large
no,
X.
it's fine. But
Sure they are.
if
Sure they
this
are.
is the case, we should not spend time discussing teams. At least, I like it. But okay.
No, I see that. It's just like,
So I want to
some point you have
understand the real
ask yourself,
situation. That's why I'm asking the question. It's a lot of beautiful things at small ends. But if we should do only that, well, let's in relation to AC, let's discuss them. If we can do both,
Can you put the figure where you have X versus Q square for EIC and so on? Okay, so at IX in EIC, and that's at square root of S of 15, the minimum Q square is 10.
what squares of S of 15?
And that's the bottom of the line.
so that's a 2.
No, yeah, but
no, this is the,
No, that's the lower range.
The hash lines.
okay, so at 30, sorry, I was looking at the other one.
Yes.
So it's what, 2 GeV?
That's a
So at
10.
30,
And
which
it
is
goes-
the smallest we have, you'll have anything, it will always be greater than Q squared.
With the higher energy setting, with the lower
With the
energy
30
setting.
GeV in the center of mass.
Yes,
Right,
yes.
I'm confused. So if you have the higher energy, if the goal is getting
Then
to
I
this
see.
region, right? If the goal is getting here,
No,
we don't have to go
it's not
to look.
But that's
So
what,
what is the
that's
goal?
what Mark said.
problem is-
Large
what is the
X,
goal?
large Q squared.
well,
Okay, let me,
for me, large Q square
Because this region here is very well mapped by coming.
Yeah, but that's fine.
That's
Yeah,
fine.
50 is.
Most settings we get to 50.
Yeah,
So
but
that's-
that was not, that's not what I
We're not
was.
talking
There
about
was-
10,000.
That's why I asked, there was last line was point X point 51, 53. That's why there is no.
Yeah, it's hard. You know, the kinematic is, you know,
The problem today is that most of the data is first, it's very close to 1 in most of the frame. And then when you get to the high X, it shoots up because you have this correlation between the two. So if you look at Slack or GELA data, the last X points are always at a very different Q squares than the previous one. So if you have a higher twist effects there, it's a little bit strange. So I think if you can extract a nice EMC effect at a fixed Q square, so you take really a band, and that only the collider gives you that. You can have a band where you extract everything at a Q square of 10 or 20. I mean, if you ask someone, people will tell you that 50 is nicer, but I think 10 is already way enough. If you can extract this band at 10, that is nice.
but
So
Jada
that's
gets
the
to
answer.
10. You learned yesterday, right?
Yeah,
Yeah,
it gets to
but,
10 for the last
I-
X point,
Not
but
much
if
of
you
that.
at 0.3 of X, you don't have 10. So it's always a slope. If you look at those data they had, it's always a slope like that in X and Q square. You always have a correlation between the two, so then that's not good.
No, you can, I mean, there are statistics with the collider up to maybe Q squared or 50 J squared at high X approaching 1. I think the biggest problem is the question of the uncertainty of the kinematics. How often you identify those events? I think there are events. They're not very, it's not, you know, not very high statistics, but there are events. So
probably
it's a detector issue and an analysis algorithm.
okay, because statistics, when you look at these points which were shown with no error bars, you should, then there still should be transitional region of large X where have some error bars which you can see.
Yeah.
And then it goes up.
Which point without error bars?
Wow, no, error bars was
Pseudo data.
Oh, but those are because there is a factor, the one that you showed.
Oh, there was this plot.
Here.
This one, or this one, there is a log 10 factor that really shrinks. Okay, there is another version of this plot where you can see the errors because I will show you maybe. I wasn't actually trying to talk about this, but maybe I will. So I will show some of these plots. Here it's very hard. It's like a feature of compressing all the data in one plot that squeezes the error bars here. It's tiny, it's precise for measurement, but there are error bars in those points.
It's really small.
Yes.
Yeah,
So because you have a factor, a scale there, it's like, you know,
the scale factor.
the
Is
minus log 10 is bigger than the reduced section by
Okay, so you're saying that actually you cannot go above 0.5.
Actually, is that true? I'm just looking at the kinematics. If I take an X of 0.9 and a Q squared of, let's say, 10 G squared,
Well, that's
the scattered electron, if it's 10 on 100, the scattered electron essentially has 10 GeV because the Y is, the inelasticity is essentially 0. And it shoots off at 162 degrees, which is not so bad. So are you sure that is just a
The problem
voluntarily
is,
cut here, your 0.5, just because of the billing?
Yes, it's because the billing features.
I mean, you know, if you would try to go to 0.8.
Yeah, probably we can. Yes, we can go to higher Q squared. Is what you mean.
I mean, for the
Or to lower.
EMC, one peaks at, you know, as the minimum at 0.75 or so. So if we, you know, I mean, just as kinematic scale.
the kinematic is accessible, but the problem is, can you actually notify those atoms properly?
Yeah, because the proton goes.
No, I understand very well, but now the question is, what about all the stuff you're producing from your atomic? That goes exactly in that same spot.
No, just goes. Sorry.
You're 160 degrees from the electron, so now you're on the hadronic side.
That is true.
And you can produce plenty of electrons out of your excited hadrons. And now you get into a completely different business. I'm not saying it's impossible to do, but
You would
the kind
have,
of
I mean,
analysis
electrons are
is
usually
I would
also
have different energy.
Yeah, electrons are usually also created in pairs, you know, and obviously played in baryon mass scale.
not necessarily, because the beam energy is tens of GeV per nucleon. So you can produce, you have a beam, you have protons that are 60 GeV. So to end up with an electron that comes out of a resonance at 10 GeV is not.
Actually, they are
It's not
not.
highly
I mean, we
favored,
can
but
talk
it's,
about this, but 0.9 means you hit a very, very hard parton, which means the electron backscatters,
Yeah.
while the proton goes in this direction. So you have all the proton shit here, you have the electron with 10 GeV in the other direction.
No,
No,
electron
they
backscatters
come back
to
to
the
the
same
same
direction
scatter, so
as
it
the
goes to
proton
the
is
same
going.
direction.
That's what backscatter
Oh,
means.
sorry, the proton goes here.
And
Oh,
the
yeah,
electron-
okay, yeah.
No, that is the problem. I mean, in principle,
How was that dealt with at Hera?
They didn't, they have crummy data.
What is the largest X Hera?
No, 0.65.
But
I think these big errors.
The horizontal-
Q-square was
So you can safely measure.
the problem is the cross section
1,000.
drops like a stone. So you're fighting.
And they have,
you're looking
of
for very
course,
few
they
events.
had a worse electron over proton ratio, right? Which is a little bit better than the IC. They had 27 over, what was it? 900.
1 TeV.
So we have in the order of, 18-20 over 250. So it's a little bit.
If I may, on a slightly different topic, you repeated several times that we need to confirm what Hermes measured in with the nuclear fragmentation functions. I don't think we need to confirm anything. I mean, there are data from SLAC, from EMC, from Fermi Lab that show, and from JLab that show the same trend. So I don't think there is anything to confirm. There might be things to measure more precisely, but
Well,
No,
measure
no,
at higher
no,
Q
no.
square. And
No, no.
These data is
I
mostly
think
pretty modest.
Point is that all the data show that energy goes up. Nu reaches about 100 GeV. Nuclear effects in longitudinal fractions dissipate. So
no, that's not true actually.
about 200 maybe. Again, it's NMC data.
No, actually, the data shows that it kind of saturates around 90–95%, and you always left with the remaining absorption, which could be an initial state effect or something. But, I don't think the data actually rules that it just goes to one. There is nothing.
Okay.
And
Okay, data which has
on top of that, if you look at the E665 data, what it shows very clearly is that, and that comes back to the point I was making about the surface event. In E665 data, they measure the number of protons that come in the backward region. So it's kind of a centrality measurement. And if they measure 0 protons, the xenon looks very similar to the deuterium, no nuclear effect. Now, if they start to measure 1, 2, 3, 4, 5 protons, the nuclear effect starts to show up. And the thing is, if you look at the distribution of the number of protons, it's decreased exponentially. So when you average all of that, it looks like there is almost no effect. But if you start to select events that with central events, then you start to see nuclear effects very strongly, even at news that are.
what quant.
It's like 20–30% absorption. It's not a small thing
Absorption for
of the
total
nuclear hadrons.
density
Forward headrows.
or forward headers.
Yes.
After what?
And so E665, I don't remember the energy, but it's hundreds of GeVs, so it's not. It's like what's it been 400 something grams. So no, the nuclear effects are there. I mean, this has been seen many times. Obviously, E665 data is very. The statistics is terrible.
No, I think
have like 2,000 events. But
We'll know more about this soon from LHC.
no, LHT will not tell you anything about this.
Multi-peripheral collisions.
It's just.
In multi-peripheral collisions, you will be able to look for fragmentation jet fragmentation.
I'm waiting to see, because frankly, all that I have seen from previous, we discussed actually last week even about that. And, I think all the previous stuff in ion-ion collision has shown to be very complicated, because you have much more constraint when you are working with electron scattering.
Yes, that's true.
So maybe ultra-peripheral will be able to progress and start to give some good information, but that remains to be proven.
But anyway, you're saying that we are talking about 10% effects, not 50% effects on the compass. Unlike
Hermes has 30 or 40% absorption, but again, this is integrated over all the volume. So if you think about it, if you look at the geometry of a nucleus, you say, okay, all the peripheral nucleons are like have no effect, so they represent like 30% of your nucleons. And at the end, you say, okay, so on the rest, so it means that if you're hitting something in the back of the nucleus in Hermes, you have 100% chance to be absorbed. You're never making it out. So and the Hermes, there are news that are bigger than 10 GeV. So you were talking about quark of more than 10 GeV that has 100% chance to be absorbed. So it's not, we're not talking about small effects. And in E665, where we are talking in hundreds of GeVs, when you start to select central events, then you start to see 20, 30% absorption. So I think it's non-negligible effect. It's slightly different than NPDF, but as you said, if you want to have all of this working together at some point, you
need a precise measurement.
I think it will be very important to understand much more. AIC certainly wasn't so discussed as a branch X function, but if we know that X, say above 0.5, I don't know, doable business precision, this impacts on discussion of fixed target products. There is still small chance.
Yeah, but I think the question from was very relevant is what are we going to have with fixed target, and how much more do we need with the IC? Because when you look at all the 12 GeV physics, we're going to have some stuff. And the question is what more do we need?
I am not thinking about nuance. Compass exists.
If compass does measurement, that's
Gillard will not be able to measure an open charm. So open charm will be able to.
I mean,
Compass will do less than
what
EIC.
what we see now is that, especially at LHC, there's all this idea about after LHCb that they mock up fixed target experiments, right? By doing gas targets in or using the halo with their crystals or something. Maybe on the long term, one can think about something at an electron-ion collider. If you want to reach very low energy that you actually put gas target in, then you have fixed target. Question is, can the detector cope? I mean, LHCb is good, very forward coupling.
So can I ask, just switch gear a little bit? We discussed a lot sometimes about this FL problematic. So FL is certainly a measurement that can we improve also upon hair on the free proton. So, but on the other hand, PI and all the fitters now say, give me what you have. So they don't really want structure functions, they want cross sections, right? So what actually FL on itself buys you on the fits? So do you need FL for?
That's a good question. I want everything that can be provided within reason, within a reasonable time frame. As we do the fits up to next in order, and depending on how we write the FL, right? If you go to see how the FL looks like at the first order, that's not zero. You have a gluon component entering and the quark component. Okay, that does not happen at the lowest possible order in the theory for us. So it is an easier way of accessing the glue, sorry. But it's true that the physical observable is your cross-section, and extracting FL requires that you run with different centers. So how well it can be done, the structure of FL, we don't know until finish. In principle, I thought it would be better, should be better than Hera, because they didn't run enough, and if we know how long we have to run and with what, then we can do it.
Okay, but what I mean, it's like it's very interesting on its own grounds because you measure the structure, function, and the precision. But to access the blue ones, for instance, you may use the charm, as we learned here, right?
Yes, high X.
So
At high X.
yeah.
But if I want to go low X, FL in principle is more sensitive to the glue than F2.
But, so whether we're talking about extracting FL or measuring cross sections, the question really, I think, is what's the lever arm in epsilon or
basically
or
you give cross
the Y,
sections in the lever arm.
the lever arm in Y, and also not just the kinematic lever arm, but what do the statistics look like? Because as you try to extend the range, whether you're the high end or the low end, the luminosity is dropping. So
The same as what happened at therapy.
yes, and so
You
so
have
part
one
of it-
point which is precise and 2 points.
I mean, the FL measurement or the Y dependence was what, the last 6 months of 10 years of running. I mean, I think it's clear that it needs more than that. Whatever the detail, the fine details of luminosity versus S and all that.
But we know, that's my point. Now we know we need more than that, so
Yeah.
we can do it.
What do we know about polarized GPF and polarized nuclear? You know anything?
Honestly, I ask about it because I never done polarized. And what I heard is you can only technically polarize so far very light nuclei, so you have not such a strong effect. That's as far as I know.
Well, there are effects predicted
Yes,
in lithium.
You should-
So,
yeah, but that's still a light nucleus.
I
That's
mean,
A
there
equals
are-
6 or 7. It's not 5. You cannot polarize lead.
You can
polarize
pull-
anything.
you can pull the-
problem is
the-
the slightly different. Is that the polarization is focalized in a few nucleons. So if you can polarize I don't know, xenon, whatever things
As
like
long
that.
as it's odd A.
But they didn't
Not
polarize it.
zero.
Oh, in the collider, I don't know.
No, xenon you can, it's spin zero.
No, well, you have to look at the isotopes.
There are a lot of xenon isotopes. I'm sure they are not going to spin zero.
Okay.
But you still not polarize
You can
all.
do this.
And I don't think there's any
Depolarize?
real
So-
fineness.
What's the problem is for keeping them polarized?
There's a
The ions.
Yeah.
No, I mean, it's just like, I think, we talk about neuron and we talk about
Helium-3.
helium-3.
well,
But
the-
as you go heavier, this is just not,
Well, it's
it's just not good. You have
it,
also to have a source, first of all, which creates polarized.
I think with the figure A, you can whatever you can produce, you can accelerate. It's the same principle of why it's so hard to control the deuteron polarization. You have the figure A.
But it's not.
But the sources will be very unique. So
Yeah,
and not cheap.
You
but-
need a specific source for every nuclei you want to make.
Intensity, yeah, so this is,
so you
No, that's
you have to really want it.
That's not
This
your
is-
one thing.
no, this is, but, typically you do set target where you have target where you
No, but the problem with polarized nuclei is if you polarize a nuclei that has spin half, let's say, the heavy nuclei, more or less when you look at the nuclear structure, what happens is you have one nucleon that is polarized and all the rest is like normal. So you have a dilution factor that is gigantic. But I was talking with Zinedine the other day, and he was pointing out rightfully that actually if you put that together with tagging, you might be able to actually pick up the one polarized nucleon.
Well, so you have a one. Let's just say you have a 1/A dilution, and then you're trying to measure a nuclear effect on top of that. So then it becomes a question of systematic errors. Can you really pull out signals?
I mean, if you
So
send
one of the questions with the
Yes.
EMC effect is, do you have the effect if you look at polarization? So if you look at the
but
axial
that
charge
might
now,
be enough
do
to
you
look
have
at the
do you-
Deuteron, right?
Well, there is no.
Well, that's a good start, but
No, well, but basically, problem is small magnetic mode for the Jupiter. That ways.
that's acceleration.
Use of Siberian snakes, not possible. That's why, but there is another method which screens the suggested. So
No, but we assume we have it. The question is, I mean, if you want to look at nuclear effects, looking at it in the deuterium is not the best place.
No,
If you want to look at nuclear
So-
effects,
no, it depends. Well, for instance, polarized deuterium is best place or the only place where we have a chance to measure shedding effects on the deuterium practice, because we measure difference of cross section asymmetry, longitudinal asymmetry. Only contribution to longitudinal asymmetry comes from shedding effects. There's no shedding effect is 2-3%.
I mean, here's a possibility. If you have an odd A nucleus where the last nucleon is in 3s or 4s, whatever, it has it actually lives inside the nucleus more than some of the other shells. So it may actually be a way of probing the inside of the nucleus with more specificity without any tagging or anything else, just the fact that you're doing a spin-dependent cross-section. So the effects, although they're still diluted by 1/A, the nuclear effect is amplified, perhaps.
that's the good thing about tagging. Now you kill the.
Well, it doesn't have to be tagging, it just has to be polarization.
We don't
If it's an
understand
S shell,
we can do X.4 with unpolarized case.
okay, let's thank our speaker and we reconvene this afternoon to structure these conversations.
You ask a question, it's like opening Pandora's.
Charles,
And specifically
wondering.
said, discuss this over lunch on Sunday.
one generator, someone who knows about the charge.
No, I think that's discuss this over lunch. That's for sure.
Yes,
You're right.
So-
You're right.
I have,
Like if I look at the old Jaeger document from this electron scattering, they have Wood-Saxton and all kinds of potential, for every nuclei, but about the deuteron, they are pretty cryptic.
well, the problem with the deuteron, I think, is that we need to redo the analysis in the light cone framework where you only extract a 2D distribution.
The transverse, what?
The transfer.